Okay, so we're going to talk about concavity and the second derivative test. Let's begin just by thinking about a graph here. This graph represents the position, the distance of a car over 60 seconds. If we take a look at the derivative of this, remember we have the tangent line here for any point on here, and the slope of the tangent line is measured by the derivative, then the derivative looks something like this. And we can see that this makes sense. Okay, if here this function is increasing and it continues to increase the whole time, so we expect the derivative to be positive the whole time. Here the velocity is not increasing very much. Here it's increasing by quite a lot. We can see that velocity go up right here, and so this is our derivative, and it represents the velocity, and everything seems to work out great here. What about if we take a look at the derivative of this function? What would that look like? Well, we can see that this is increasing until we get to about right here, and then it starts to decrease. So we would expect the derivative of this to be positive up until we get to about, I don't know, 25 seconds or so, and then we would expect it to be negative. And so if we take a look at the derivative of this function, it does exactly what we expect it to. Now the derivative of velocity is acceleration, and so we are looking at the acceleration graph right here. It's positive until we get to this point right here, and then it starts to be negative. Okay. Let's see if we can see some relationships between the acceleration graph and the original function up here. Now notice what happens right here. If we look at this graph, we can see that it certainly has a certain type of shape up until we get to about right here. And it seems to be kind of smiling right here. So it seems to be kind of smiling. We actually call that concave up. And then at this point, it starts to sort of frown a bit. And so we have concave up until we get to here. After that, it's concave down. Concave up is sort of a smile shape, and concave down is kind of a frowning shape. And remember, it's at this point right here where we change here down here in the second derivative graph. It changes from being positive to being negative. And so it seems like what's actually going on here is that wherever we have this smiling shape, the second derivative is positive, and wherever we have this frowning shape, the second derivative is negative. So concave up, second derivative positive, concave down, second derivative negative. And it turns out that that's exactly the case. So I'll remind you that if we wanted to look at increasing, decreasing intervals, then we would look at the first derivative. But the second derivative will tell us about concavity. We can see that in this graph right here that we have this frowning shape until we get over to about right here. This is a place where the second derivative would be negative, you know, from negative infinity all the way over until we hit to right about here. We can see that the second derivative would be negative there, and this is where it's concave down. And after that, the graph starts to smile, and we call that concave up. And that's where the second derivative is positive. Looks like that would be from 0 to positive infinity. So let's talk about something called the second derivative test. Let's start off here by saying we've got a c, which is a critical number, where the first derivative is equal to 0. Now remember, what that implies is that you've got a horizontal tangent line. And if the second derivative is negative at c, then there's a relative maximum at that point. And if the second derivative is positive at c, then there's a relative minimum at that point. Now this is actually fairly easy to see. If we go back up here and look at this, let's say we've got, so this right here would be our highest point. Looks like what, well, maybe a little bit over. This right here, so it looks like our c would be some number right down here. If we've got a horizontal tangent line here, then that kind of tells us that, okay, we've got a relative maximum, and we don't really know which one it is. But the fact that the second derivative is negative there tells us that this thing is frowning, and that implies that, well, it's pretty much got to be a maximum. There's no way that this can be frowning if it's a minimum. And the same thing over here. If I've got a critical number And right down here, I've got that point on the graph, and I know I've got a horizontal tangent line at that point. The horizontal tangent line tells me that it's a maximum, a relative maximum or minimum. It's not always, but it could be a place where there's a relative maximum or minimum. But if I know the second derivative is positive there, then this thing's got to be smiling at that point, and there's no way you could get a relative maximum if the graph is smiling. So the second derivative test basically says that, okay, you got a place where you've got a horizontal tangent line. If the second derivative is negative, we know the graph is frowning. That means there's a relative max. If the second derivative is positive, we know that the graph is smiling there. We've got a relative min. Okay, so we want to analyze the graph of f of x equals negative x to the fourth plus 4x cubed plus 5. And what I'm going to do here is I'm going to just sort of take it through all the stuff that we know. I'm going to think about critical numbers. I'm going to think about increasing and decreasing. I'm going to think about concavity. I'm going to look at relative maxes and mins. And I'm going to take a look at what the graph looks like. I'm just going to kind of put it all together here. So how about if we start off by thinking about increasing and decreasing? Now remember, this is going to come from the first derivative. Okay, so I'm going to find the first derivative, f prime of x. Well, okay, it looks like that's fairly straightforward. Negative 4x cubed plus 12x squared. There's my first derivative. I'm going to factor it down a little bit. I'm going to factor out a negative 4x squared, which gives me an x minus 3. All right. And I'm going to set that equal to 0 so I can look at my critical numbers. And it looks to me like what I've got is okay, from here, I'm going to get x equals 0. But remember, that's an x squared. So that's actually with multiplicity 2. So I've got x equals 0 with multiplicity 2. And I get, if I set this one equal to 0, x minus 3 equal to 0, gives me x equals 3. And I know that's with the multiplicity 1. We usually don't write that. Okay, I'm going to make myself a sign chart here. And so I know 0 is an important number. I know that 3 is an important number. All right. I'm going to put up here, this is the sign of f prime. Okay, so what I know is that at 0 and 3, f prime is equal to 0. So I'm going to just sort of indicate that here. And now I got to go choose a test number. Let's choose a number like maybe 1. That's going to be my test number. And what I mean by that is I'm going to take 1 and plug it into the derivative to see whether it's positive or negative. And I can do it here or I can do it over here. It doesn't matter. They're both the same thing. I'll just do it here. It looks like this will be easier. Negative 4 times 1 cubed plus 12 times 1 squared. Well, that's going to give me a positive 8. And so I know that I've got pluses right here. I know that the first derivative is positive between 0 and 3. Well, now I can do the same thing over here. I could choose a test number like, I don't know, negative 1 or so, or any number that's over here. I could do that. I could plug it in up here and I could go do that. Turns out that that's going to be positive. But I also know that this multiplicity is an easier way of doing that. If it's even multiplicity, the sign doesn't change. The sign only changes at odd multiplicity. So I don't expect for the sign to change right here. And so I see that I get pluses. And really, you can do that either way. You can just plug that negative 1 in and get that, or you could just kind of think about the multiplicity thing. And the same thing over here. You could just choose a test number. You could choose a number like 4 or so, or whatever. Plug it in up here. What you're going to find is that it's going to be negative. I can see that pretty easily because x squared is always positive. I've got a negative out here. 4 minus 3 is positive, so a positive times a negative is negative. Or you can say, hey, I know that's odd multiplicity, so I expect the sign to change. Either way, you can see that you get negatives there. So what have we done? Well, we've pretty much identified where this thing is increasing and decreasing. And it looks to me like it's increasing from negative infinity. Remember, this thing just goes on out forever. So negative infinity over to 0. And also from 0 to 3. And it looks like it's decreasing from 3 to infinity. Now, all I'm doing here is I'm just kind of reading this straight across. Remember, this is an x-axis here. And these are my important numbers, 0 and 3. Don't get that mixed up with your test numbers there. So negative infinity all the way over to 0 were my pluses. And then from 0 to 3 were pluses. And then from 3 to positive infinity were my negatives. And that's how I ended up with this. Okay, great. Now I'm going to just sort of put something down right over here. I'm gonna go off to the side right here and just recognize something real quick. I recognize that in this graph I had increasing, hit a tangent line that's horizontal, and then decreasing. In other words, it was going up, hit that top, went down. I see right here that I've got a relative max. A relative max, and that's occurring at the x value of 3, and the y value would be f of 3. And remember, to get that y value, you always go back to the original function up here. So I would stick 3 into this function up here, and turns out that that's going to give me 32. All right, you can just throw that straight into the calculator. We end up with the point 332. All right, so we know some stuff here. We know where this function's increasing. We know where it's decreasing. We know that it's got a relative maximum, and we know what that point is. Okay, well, let's see what else we can do. We could talk about concavity. Okay, so let's just remember what our first derivative is. Our first derivative is negative 4x cubed plus 12x squared. Concavity deals with the second derivative. So let's go ahead and write down the second derivative. The second derivative is going to be, let's see, looks like that will be negative 12x squared plus 24x. Okay. And basically, we're going to do something very similar to what we just did right here. All right, we're going to find these places where the second derivative is 0, and kind of pick out those important numbers, and then we'll do a sign chart, and we'll be able to tell where the second derivative is positive and where it's negative, and we'll be able to write down our intervals of concavity from there. So I'm going to just clean this up a little bit. Let's see, I'm going to factor out a negative 12x, which gives me an x minus 2 here. I'm going to set that equal to 0. And it looks like I get two numbers here. Now, these aren't critical numbers. Critical numbers come from the first derivative. These are points that are just sort of points of interest. If the concavity actually changes, then that's called a point of inflection. But I don't really know whether the concavity changes yet. At this point, I'm just writing down a couple of numbers that come from setting the second derivative equal to 0. And it looks like I get x equals 0, and I get x equals 2. And I'll just sort of make a mental note here that both of those have multiplicity 1. Both of those have odd multiplicity. And I will go in here and I will make myself a sign chart. And I'm going to try to do this sort of similar to the sign chart up here. So my 0 is here. So that was an important number. I'm looking at 2, so 3 would be right about here. So I'm going to come on back a bit. 2 is over here somewhere. Okay. And I'm going to go in here and I'm going to do pretty much the same thing I did up here. I'm going to choose a test number. Let's choose a test number of something like 1. Okay. So I'm going to take 1, I'm going to plug it into the second derivative. Remember, what I'm doing here is I'm looking at the sine of f double prime. And so 1 goes in the second derivative, and it looks like that's going to be positive. So second derivative is positive here. And remember, that means that's where that graph is smiling. Now, because each of these had odd multiplicity, I expect to have, the sign changing on both sides. You can go back and choose some test numbers and just verify that. Maybe a test number of -1. Plugging it over here, you're going to see that this is going to be negative. Test number of maybe 3. Plugging it up here, you're going to see this over here is going to be negative. Okay. And it looks like I can go ahead and write down something about my concavity now. I know that it's concave up between 0 and 2. I know that it's concave down when it's less than 0 and greater than 2. Now, it's a little hard to do at this point. You may be able to sort of imagine this, but we know that the graph is increasing until it hits 0. And we know that it's frowning until it hits 0. And then at 0, it is still increasing once it gets past that, but it starts to smile. You can kind of imagine what that graph is going to look like. Frowning, and then starts to smile. And it keeps smiling until it hits 2, at which point it starts to frown again, and it's still increasing, and it hits a relative max at 3, and then it starts to decrease again. So you might be able to imagine what that looks like, just by looking at that, but we'll sketch some graph here in just a minute. At the moment, let's just go ahead and write down our concavity. Okay, so we know that this is concave up between 0 and 2. And again, I'm just reading from my x-axis here. I'm just going straight across. It's going to be concave down from -infinity until I hit 0. -infinity to 0. And also from 2 to positive infinity. Okay, I'm also going to write down just a couple of points here that seem to be of interest. Looks like I should be interested in what's going on when x is equal to 0. And it looks like I should be interested in what's going on when x is equal to 2. Right, those are a couple of points that kind of popped up over here, a couple of x values that popped up. And so if I go back and plug 0 into the original function, looks like I'll get 5 right here. If I plug 2 into the original function, we'll throw it in the calculator. That's going to end up being 21. And so I've got a few points right here that I can play around with. So let's see if we can start to put some of this together. Okay, so I'm going to go in here and just sort of see if I can sketch some of this out. And yes, I know we have a calculator that we could go in and let the calculator do all this, but it's worthwhile to kind of get an idea of what this looks like just without using all the technology to do everything for you. It sort of gives you a feeling for the behavior of that function. So I'm going to start by kind of putting in some points here that have just shown up. The point 0, 5. So I'm going to say 5 is right about here. So I've got a point right here, and that's the point 0, 5. I know that's popping up on my graph somewhere. I've got the point 2, 21. So, okay, so if that's 5, then this will be about 4 times as high. It goes up to about right here. Go over a couple. Let's say we've got right about here. So this would be 2. Okay, and up here would be 21. So this is the point 2, 21. And I've also got the point that came from over here, 3, 32. So I'm going to go over one more. And 32 is going to be up a little bit higher than that. So I'm going to go on up to about right here. Okay. And that's the point 3, 32. And I'm really just sort of sketching these things out. I know those are 3 points that are on my graph. Of course, I can always go back and find other points just by plugging into the original function. But these are sort of where important things happen. Now let's think about what is happening then. What do I know happens before x equals 0, like over here this way. What's happening before this? Well, one thing I know is that the function is increasing. So it's going up. And I also know that the function is frowning. So it's increasing and frowning, which means that it's looking something like this. Okay, it's increasing, but it's kind of frowning. Now at x equals 0, it starts to smile. It starts to become concave up. But it is still increasing. Right after 0, it is still increasing, and it's going to continue to increase until I hit 3. But it's only concave up between 0 and 2. So it's going to start to smile at this point. It starts to be concave up until it hits this one right up here. And at this point, it starts to frown. It starts to be concave down, but it's still increasing until I hit my relative max. So now it's sort of frowning. And then after 3, I know that's a relative max, it starts to decrease. So at that point, it starts to go down, and it goes down forever. So even without the use of a calculator, I've been able to sketch a rough graph of this just by thinking about what happens at all those key places. Now, one thing I will point out here is that, you know, I can see I got critical numbers, right? This was a critical number here, and I have a horizontal tangent line there. I got a critical number right here, and I had a horizontal tangent line. So, okay, those came from the first derivative. Here, the concavity changed. The concavity changed from smiling to frowning. The concavity changed here as well. It changed from frowning to smiling. And so I've got a couple of points here where the concavity changes, and those are called points of inflection. Points where concavity changes are called points of inflection. Some people just call them inflection points. And so, you know, sometimes you may be asked to find the points of inflection. And what that generally means is you're looking at the second derivative, you're doing this sort of game right here, and you're just looking to see, okay, at what places do we have a switch of signs? Okay, let me point out one other thing here. Remember we had a critical number right here, which was at 3. And, you know, we had a critical number here too, but we kind of knew that nothing really was happening here because of what's going on here. We had a critical number 3, and we could tell from the first derivative that that was a relative max, right? Looking at the signs of the first derivative, we got that. We know that that's a relative max right there. But we could also use the second derivative to figure out the same thing. Here we've got the critical number 3. Remember that our second derivative was negative 12x squared plus 24x. And so if we were to go in here and find the second derivative at 3, we get a negative 12 times 3 squared is 9 plus 24 times 3, which would be, let's see, that's what, negative 108 plus 72. And so whatever that is, that we can see that that's going to be negative. Second derivative is negative at 3. And remember that the second derivative test also tells you about relative maxes and mins. So if we didn't know that, if we didn't have this information over here, and we didn't, or maybe we just skipped over that or something, we didn't point out that that was a relative max, we could have gotten that information from right here. We've got a critical number, we've got a horizontal tangent line, and the second derivative is negative there. And remember that the second derivative test says that if we've got a horizontal tangent line and the second derivative is negative at that critical number, then there's a relative max. So yeah, I mean, we don't really have to do this because we already knew that, but we can see that everything sort of works out the way we expect it to here. So I guess the very last thing that I'm going to do is just sort of verify that my graph looks right by going into the calculator, and I'll let the calculator graph it. So I've already put this into my calculator, and I need to think about a window. So I know just by kind of looking at those at all my points that show up, all my important numbers, I know I don't need to go too much more to the left of 0. I don't need to go too much further out than 3. I'll go a little bit. I know that I don't need to go too much higher than 32 for my y values, and I'll just go down, maybe down into the negative somewhere. So I'm going to go into my window, and I'm going to put in something like, I don't know, negative 5 for my x, and I'm going to go up to 5 for my maximum of the x with a scale of 1. Y, man, I don't know. I'll go maybe something like negative 10. I'll go up to something like maybe positive 40, and y scale of 1's fine. And I'm just going to take a look at that graph. And wow, pretty amazing. All right, anyway, that's it for this video, and I hope it's been helpful, and see you in the next one.